Good morning. Just got out of bed a minute ago. All right. Kind of a tough look, but it's because you were up late finishing all your homework that you needed to get done, right? Yes, exactly. I knew it. All right. Let's go for it. I don't have a warm up on this one today because we have a lot to go on this one. There's a lot of things to get through, so I want to make sure we do. Just kidding. We don't have a warm up because I forgot to put one on there. But I at least made it of getting the notes on there. So we'll call that a win. And I'm sure you were devastated that there was no warm up for you to do prior to class. But so yesterday I talked about our sequences, just kind of a basic idea of what they are and how to write out the terms of a sequence, a recursive sequence and how that works whenever it's based on a previous number, and a little bit of factorial stuff with just knowing what a factorial is and then describing as well. So for today, we're going to talk about sequences converging. So converging, a nice vocab word that we know from talking about limits. And if a limit converges, right, we actually get some number, some version. Why does 0 factorial equal 1? Okay. So I think the best, there's various explanations I could give you from different aspects. So here's the one that I think will work best for you guys. So another thing that factorial is used for, you might remember from maybe geometry, is like permutations and combinations. And so if I say, for example, you're trying to open a lock that has 4 digits on it, like one of those locks where you spin the numbers or whatever. And if you think of, well, how many, maybe that's not the best option, but the point is, if I have a various number of things that I want to order, right? Like if I have the numbers 2, 6, 1, 3, and I want to know what are all the different orders that I could put these in. So it could be in the order 2, 6, 1, 3. It could be in the order 6, 2, 1, 3, or the order 1, 3, 2, 6, or the order 6, 1, 2, 3, or et cetera, et cetera, et cetera. Just all the different possibilities for the orders that I could put them in. How many possibilities are there? Well, there's actually 4 factorial possibilities because there's 4 spots. And so 4 times 3, 12, 12 times 2, 24. So if I listed out all the possibilities, there's 24 orders, right, for 4 elements. And so that works for everything. And then same thing, if I just have a number 6, how many different ways are there to order this? Well, there's only one spot. So there's only one possible order. So that's why 1 factorial is still just 1. Now, if I don't even, so now let's go 1 down. Let's go to 0. So if there's 4 elements, the amount of orderings we can do is 4 factorial. If there's 1 element, the amount of orderings we can do is just 1 factorial, which is 1. But what about if I had 0 if I have nothing, I don't even have a list of numbers. I don't have a list of anything. How many different ways are there to order nothing? Well, there's only one way to order nothing, which is that you can't, right? So if you think of the factorial as like meaning number of ways to order this many things, so the number of ways that I can rearrange nothing, well, there's just one way to do it, and the one way is that you can't do it. So I think I know that's still kind of confusing and weird, but I think that's kind of the most intuitive explanation. Is that, I don't know, did that actually resonate? Clip that, please. I should see way more emotes in the chat right now for that good math that I just did. Thank you, Tyler. Not like this. That works too. Okay. So I hope that actually helps. Again, there are other various explanations I could give, but I think that's the one that makes the most sense, just kind of on an intuitive basis. And it's something you're sort of familiar with. You guys remember maybe that you did permutations and combinations in geometry. Sorry, accelerated geometry. Don't want to downplay your accomplishments there. Okay. I know, right? All right, so we'll say that's our warm-up for today. It's talking about why 0 factorial equals 1. Thank you for reminding me, Emily. But so back to this. We're going to know how to write out an equation of a sequence. If we see a sequence and we're trying to figure out what is the equation that makes this sequence. So a couple quick things before we actually dive into problems. The limit. So kind of a similar definition from limits that we know before. So we say if a sequence has a limit L, then we can say that it converges to L. And if a sequence does not converge, there's only two options. Every sequence or every limit, either it converges, or if it doesn't, then we say it diverges. So a nice little theorem. If f is a function and the limit is L and an is a sequence, so that an is the same as that function, then the limit of an is L. Okay, so basically kind of what this is saying is if we have some function, any function, and we know that it has this limit L, well, we could instead turn that function into a sequence. So, if I had a function 3 over x, and if I knew that that has a limit, well, then if I say, well, actually, I don't want it to be a function anymore. I want it to be a sequence. So I just kind of changed some stuff to make it a sequence instead. Well, the sequence has the same exact limit that the function would have. It doesn't matter which way I think about it, whether I'm writing out the terms of a sequence or whether I'm dealing with the function, they still have the same limit at the end. That's all that's saying. Is L a thing or is L a constant? L is a constant. Yeah, whenever we talk about the limit equals an actual constant number. Unless I'm misunderstanding your question. Like E. Oh, I see. No, L doesn't represent an actual number. We're just using L because it's short for limit, right? So L could be anything. It could end up being 3 or 5 or -10 or 1/1000th. E is a constant, yeah, but I think what they're asking is, are you asking if L represents a specific number? Like pi represents 3.14 or like E represents 2.718? Is that what you're asking? No. No. That's not what this L is. We're just using capital L to represent whatever the limit means. So determine if the sequence converges. If it does converge, state what the limit converges to. All right, so we're just doing limits. Right? So you guys were all emailing me. You were saying, Mr. Bunnis, we miss limits, and it's even worse now that we can't go to school. So can we do more limits again? So I'm like, yeah, I mean, for sure. Let's do them. So the limit as n goes to infinity. Well, currently, when I have a rational function, right, 2n over n plus 1, I'm going to first kind of think about these numerators and denominators individually. So 2n, as n goes to infinity, 2 times bigger and bigger and bigger numbers, well, that's just going to, the numerator is just going to go to infinity. And the denominator, n plus 1, so bigger and bigger and bigger numbers plus 1, well, that's also just going to go to infinity. That's just forever getting larger and larger. So I have, this is approaching, or this would be approaching infinity over infinity. But, of course, you remember what we need to do whenever we get infinity over infinity, which we also remember is called an indeterminate form. We need to go to the hospital. No, you should not go to the hospital, right? Unless they specifically tell you to go in. If you have symptoms, you call ahead of time, speak with them, to your primary care physician, then they'll direct you what to do, okay? Don't just be showing up at the hospital, you guys. Come on, be smarter. Right? But so yeah, we got to use L'Hopital's rule. So L'Hopital's rule tells us, well, just take the derivative of the numerator, take the derivative of the denominator, and see if that helps you out. So derivative of 2n is 2. Derivative of n plus 1 is 1. And so it actually did help a lot. So the sequence converges to 2. All right, so that means if I list out the terms from that sequence, right, plug in 1, plug in 2, plug in 3, and I list out all those numbers, as I go on, those numbers will be getting closer and closer and closer and closer to 2. Right. Thank you, L'Hopital, for your fun rule. Okay, determine if the sequence converges. Same thing. If it does, state what the limit would be. So you might recognize these are all of our same sequences we dealt with yesterday when we were just writing out the terms. But now we're actually figuring out if they converge or not. So 2 plus -1 to the nth. So let's just think about this one for a second. Remember that this sequence looked like if I plug in 1, I get 1. If I plug in 2, we get 3. If we plug in 3, we get 1. If we plug in 4, we get 3. And this was just an alternating sequence between 1 and 3. Those are the only possibilities we will ever get from this sequence. Because all that's happening is either the -1 is to a even power or an odd power. So it's either 2 plus 1 or 2 minus 1, 2 plus 1, 2 minus 1, 2 plus, which is back and forth forever. So we can tell just by looking at that the sequence is not approaching a number. It's not like these numbers are starting to get closer and closer to 4 always, or they're starting to get closer and closer to 2.7 or anything like that. It literally just bounces back and forth between 1 and 3. Okay, so that is not converging, right? We can tell that is not getting close to a limit. So I can just go ahead and say here, does not converge, right? Or I guess, I don't know why I wrote that all out, because you can just say diverges. Right, diverges, does not converge, same thing. Next sequence, n squared over 2 to the n plus 1. So think about this limit. As n goes to infinity. So again, n squared in the numerator, well, that'll just go to infinity. In the denominator, 2 to the nth power plus 1, well, that's also just always going to be getting bigger and bigger as I plug in bigger and bigger numbers. So I'm in another case where I wrote an ugly infinity sign and I fix it. So it's a little better. It's infinity over infinity, indeterminate form, so we can use L'Hopital's rule. Derivative of n squared is 2n. Derivative of 2 to the n plus 1. We haven't done a ton of, I mean, I know we talked about it and we've done it every now and then, but we haven't done a ton of derivatives of exponentials, right? We know that e to the anything is just the same thing. But so, brief reminder. Let's just do a general. Any number to the nth power, if I want the derivative of that, assuming I can write this, is so sort of similar to e, where it is the same thing, but then times the natural log of the base. And that's too far over for you to see. So for us, 2 to the n plus 1, so that would be 2 to the n times natural log of 2. Natural, or derivative of 1 is 0, so it's just this. So now I'm going to try this again. 2 times n as n goes to infinity. Well, that'll be infinity again. In the denominator, 2 to the nth power times natural log of 2 is just a number. So this will also still be going to infinity. All right, so I still have an indeterminate form. But remember, that is okay because we can continue using L'Hopital's rule as many times as we need. Again, the chat demands, so we will do it again. Derivative of 2n is 2. So the derivative of 2 to the nth power is 2 to the nth times natural log of 2. And then there was already the natural log of 2. So treat that natural log of 2 like a coefficient, where remember, coefficients stay there. They just get multiplied by whatever else. So natural log of 2 times natural log of 2, or natural log of 2 squared, whatever. Okay, so now this, I like this limit. It's a little ugly, but that numerator is just a constant. It's just 2. But my denominator, 2 to the nth power is going to get really large really fast. So my numerator is staying the same. My denominator is getting very, very large very, very quickly. So this limit is 0. Boom. Nailed it. Grant just barely beat out RJ there. And we would say the sequence converges to 0, or the limit of the sequence is 0. Yeah, better Wi-Fi. Oh, dang. You got that Google Fiber, man? How many times would you do L'Hopital's rule before you decide it doesn't work? There's not really a solid number. The only way that I probably wouldn't do it is if both the numerator and the denominator just had something that would never disappear. So like, for example, our numerator started at n squared. I know that after I take a couple derivatives, I'm going to end up with a constant. Or if I took the derivative again, I would end up with 0. But so if I had something like an e to the x, something that, you know, the derivative will always still, there will always still be a derivative of some kind. It'll never end. Or something like a cosine or sine, where again, like cosine and sine derivatives will just alternate back and forth, back and forth, back and forth. So maybe if you see that it's just an endless cycle, then maybe that's a no-go. I don't know. I'm trying to think of a specific example, but if you see, like I'm looking at my numerator, I went from n squared to 2n, okay, down to 2. Sisyphus, yes. This was really a Greek lesson in mythology. That was what I anticipated this lesson would turn into. Okay, so finding limits of sequences is just like finding limits in general. Write the explicit form of the sequence, determine its convergence. If it converges, state to what it converges. So I have the terms of a sequence, and I want to figure out what is the actual formula for the sequence, you know, an equals whatever, that would create this. So my goal is to figure out what the formula is. Whenever you're looking at these, especially if you're looking at a fraction, right? Maybe the rule is like, oh, just add 3 each time, or multiply by 2 each time, or something like that. But if I'm looking at a fraction, sometimes it can be a bit harder to tell. So I would say a good general rule of thumb is look at the numerators, look at the denominators. And first determine what should the rule for the numerator be, and then determine what should the rule for the denominator be. Because a lot of times that will work out. Sometimes you have to make some slight changes. But so for example, all my numerators here are 1. So I feel pretty confident that whatever this formula is, the numerator of it is just going to be 1. And in the denominator, 2, 4, 8. So the thing I know about 2, 4, and 8 is they're all powers of 2. So my denominator should be 2 to the nth, right? Yeah, 1 over 2 to the power of n, exactly. And now you can double check things, because remember, so this is my first term, this is my second term, this is my third term, this is my fourth term. Okay. So wait a minute, does this actually work? Because if I were to find a1, that would be 1 over 2 to the first power, so that would give me 1/2. Or if I did a2, that would give me 1 over 2 squared, which would be 4. So I'm missing my first value, that 1, right? This is still here. So I'm sort of on track. I'm just kind of one step ahead, where it should be that my first term, A1, gives me 1. My second term gives me the 1/2. Third term, the 1/8, and etc. Okay. Yeah, exactly. So let me fix this. 2 to the power of n minus 1. Okay, so let's try this. So a to the first power, 1 over 2 to the 0th. 2 to the 0th is 1, so 1 over 1, 1. Great. A2, 1 over 2 to the first power would be 2, etc., etc. Perfect. So sometimes you might have to bump your sequence up or down one. It might be shifted a little bit. So, oh, wait, actually, it's not exactly this, but, you know, add 1, subtract 1 in that exponent or anywhere. Okay, so this is my explicit form of the sequence. Okay, and then we have to figure out if it converges and what it converges to. Could that change the answer if it came up on a test like this? 1 over 2 to the n would be wrong. Yeah, because 1 over 2 to the n does not give you that first term, the 1. We have to have that 1 in there. That's part of the sequence. So 1 over 2 to the nth power. Yeah, it wouldn't cut it. Cool. As n goes to infinity, this limit, so my numerator is staying at 1. My denominator is rising in powers of 2. Now there's the n minus 1, but we're talking about as n goes to infinity. So my denominator is going to infinity. My numerator is staying at 1. So it converges, and specifically it converges to 0. Let's go again. So write the explicit form of the sequence. Then determine its convergence. If the sequence converges, state to what it converges. All right, so I want to figure out what this formula is. So again, I've got some fractions. So think about the numerator and denominator individually. This should help. So for example, my numerator is going 2, 4, 8, 16. Again, I recognize these as powers of 2. So I'm going to try 2 to the nth. I don't need to shift it. At all, because if I plug in 1 for the first term, it would give me that 2 in the numerator. If I plug in 2, it would give me the 4, etc., etc. So I don't need to worry about the plus 1 or the minus 1 for the numerator. Now, for the denominator, 1, 3, 5, 7, we should be able to pretty easily deduce that these are just the odd numbers. 1, 3, 5, 7. But the question is, how do I write that as an expression? Okay. So typically for odd numbers, so what do we know about even numbers? Even numbers are always divisible by 2. Okay, so if an even number is always divisible by 2, then an odd number will always be one off from that, right? So typically for odd numbers, we want to think about AK plus 2. Not quite. For odd numbers, we either want to think about, like, for example, 1, I can think about as 2 times 1 minus 1. Or 3, I can think about as 2 times 2 minus 1. Or 5, I can think about as 2 times 3 minus 1. Right? 6 minus 1, 5. 4 minus 1 is 3. Right, so 2n minus 1. So for odd numbers, we're always going to think about, we're typically going to use this expression, whether it's 2n minus 1 or 2n plus 1, depending on, again, maybe we need to shift it. But an odd number is always just an even number minus 1, if that makes sense. Well, again, do some quick checks just to make sure. A to the first power, so that would be 2 over 1, 1, great. Or A to the fourth power, so 2 to the fourth is 16. 2 times 4 is 8. 8 minus 1 is 7. So, yeah, these would work out. So this is my actual explicit form of the sequence. And then I want to figure out if it converges or not. When I see I have a rational function, right? I have a numerator, denominator. I'm worried about, or not worried, but I'm thinking, is this going to be an indeterminate form? 2 to the nth power, that'll go to infinity. 2 times n minus 1, that will also go to infinity. So indeterminate form, we're going to want to use L'Hopital's rule. Derivative of 2 to the nth, we talked about a couple times here. Derivative of 2n minus 1. I don't know what that derivative is. Someone asked Carter. He's the derivative master. So now my denominator is just a constant, 2. But my numerator, 2 to the nth power, this will be just going to infinity. So this is different. If we get just infinity, right, because my denominator is not infinity, my denominator is just staying 2, but my numerator is getting larger and larger. So no matter what, infinity divided by 2, that kind of concept, we're still just getting to infinity. All right, so if I just end up with this whenever I do a limit, then not doing L'Hopital's rule. L'Hopital's rule is specifically for if we get infinity over infinity or 0 over 0. But in this case, if I get just infinity, I'm so popular. You guys hear my phone ringing? Ooh, actually, that's my doctor. Then this diverges. Okay, so this sequence does not have a limit. This sequence just diverges. I know, big yikes. I think they're calling me to tell me my surgery is rescheduled again. That's my assumption. Again. Third time. All right, let's go on again. So I'm writing my rule. I'm looking at kind of the pattern here. These are just counting by twos. These are not powers of two. These are multiples of two, right? Just like 2, 4, 6, 8, 10, 12. And my denominator is just increasing by 1 every time. So even though my first term is 1, like that kind of throws off like, well, it's not a fraction. But we can kind of see what the pattern should be, is that the numerator is just counting by twos and the denominator is just counting by 1. So instead of 1, I can think about it as 2 over 2, if that helps me make sure the pattern works everywhere. So numerator is 2, 4, 6, 8, 10. Remember, those are just the even numbers. What do we know about even numbers? They're just divisible by 2, right? Multiples of 2. Weird flex. Which part? Did I have a lot of friends? Just telling it like it is, you know. And my denominator is just counting by ones. Okay, but remember, this is based on the 1, 2, 3, 4, 5. So the first term, I know I'm plugging in 1. Right? So if I want to get 2, when I'm plugging in 1, well, then I should be doing n plus 1. Not n plus 2, because we don't start by plugging in 0. Misclick. Sure. Yeah. Okay. Yeah, and then double check. It does work for everything else. So you can do all of them. You can pick a couple, whatever. But for example, like A3, 2 times 3 is 6 in the numerator. 3 plus 1, 4 in the denominator. We're on a great roll. So the tough part will be, a sequence probably won't look like this, because you might notice that sequence, those fractions are definitely not simplified or reduced, besides the 1. So the real question would be, could you look at this sequence and determine that this is the correct explicit form? Because it's the same sequence. All I've done is just simplify the fractions. Okay, so it's not only just about pattern recognition, but also kind of have to think about recognizing patterns that aren't even technically there, but imagining, wait, could this be a fraction that was simplified to then make this? So you're excited. Let's do the limit. This would go to infinity over infinity. So I'll use L'Hopital's rule. Two over 1 is 2. So I know that this sequence converges. Okay. So for this sequence, I'm going to look at my numerators first. 4, 9, 16, 25. Okay, so it's not just even numbers, not just odd numbers, not powers of anything specific. But hopefully we can realize that the common thing that 4, 9, 16, and 25, the property they all share is that they're all perfect squares. Right? 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, 25 is 5 squared, etc. So my numerator, I'm thinking, should just be n squared. And that would work for my first term so far too. If I plugged in 1, 1 squared would be 1. Okay. Now for 3, 7, 15, 31. Right, this one's a little trickier. I'd be interested, I don't know, does anyone have an idea or think they know for the denominator? I will strategically drink some water to allow you time. All right, that was squared over 2 to the n minus 1 on the outside. Yes, exactly. Okay, nice. Hold on, I lost my smart notebook. Come back. Okay, are we good? Can you guys see that again? I think so. Okay, yeah, so exactly what Hayden said, I think. 3, 7, 15, 31, these are all they're all 1 less than powers of 2. Right, 3 is less than 4, 4 is a power of 2. 7 is 1 less than 8, 8 is a power of 2, etc. So what this is 2 to the nth power and then minus 1, not minus 1 in the exponent, just minus 1 kind of on the outside. It's been made. I know. I could tell because you always still have to leave for music. Oh, shoot. Should I have done a different streaming schedule because it's Wednesday? We have early release, man. I'm excited. So taking the limit, this would go to infinity over infinity, indeterminate form. So let's do L'Hopital's rule. Two n over 2 to the nth times natural log of 2. This would, again, go to infinity over infinity. Yeah, you're late, man. Mr. Keeler was supposed to come get you. I don't know what happened. I guess he forgot. So we'll do L'Hopital's rule again. Derivative of 2n is 2. Derivative of 2 to the nth times natural log of 2. So that would be 2 to the nth again. Natural log of 2 times natural log of 2. Yeah, I think so, man. I think you're done at 10:30. Numerator is staying the same now. Derivative, or the denominator, will still go to infinity. So this limit is 0. Nice. Good stuff. I'm going to help RJ out here. Okay. So last one of these. I know we've done a lot of them, but I want to just get in a good habit of recognizing the patterns and then also just practicing using the limits. But this one's tricky. Okay, so I've got very different things going on. My numerator is not only just changing, it's also alternating between positive and negative. I can see all the opticals in my way. Okay, so purely based on the fact that this is alternating between positive and negative, I know that, so going back to whenever we had that sequence that just alternated between 1 and 3, 1 and 3, 1 and 3, because there was that piece of it that just alternated between adding or subtracting, right? So yes, absolutely, you smell a -1 to the power of n. So that's definitely going to be a part of our equation. Now, be careful. Sometimes you might need it to be n plus 1. But this particular sequence starts with a negative number. So I know that whenever I plug in 1, I want my answer to be negative. So this would make sense that -1 to the first power stays negative. But maybe if this was the other way, where it started positive and then went negative, I would do -1 to the power of n plus 1, for instance. Okay. So besides that, now if I'm just looking at 2, 8, 26, 80, 242, hopefully if you're kind of thinking along the same lines as our last expression, okay, that what do all these numbers have in common is that they're all 1 less than a power of 3, right? 2 is 1 less than 3, 8 is 1 less than 9, 26 is 1 less than 27, 80 is 1 less than 81. So these are all just powers of 3, but then subtracted 1. So 3 to the nth power, but then take away 1. For the denominator, 1, 2, 6, 24, 120. So these are not just skipping. They're not just powers. So my hope is that in a little, after a couple weeks or so, you'll absolutely recognize these numbers. But for right now, since we just started talking about it last lesson, I doubt it. 1 I could recognize as 1. 2 I like to think of as 2 times 1. 6, aka 3 times 2 times 1. 24, 4 times 3 times 2 times 1. 120, 5 times 4 times 3 times 2 times 1. So my denominator is just n factorial. And so this would be, if we take the limit. Whoa, no. Yeah, Reese, that's too many. You don't want to do n factorial factorial. That would be crazy. That would be like a super huge number. That's insane. Yeah, so that would mean you would take 120 and then do the factorial of 120. Wild. All right, so like it says, I'm going to graph this real quick. So I'll use x instead of n, whatever. It's factorial. We're going to, hold on. Wait a minute. Table. Sorry, it's being weird. So if I plugged in 1, I would get negative 2, 2, 4, 3, 4, 5, 6, 7, 8, 9, 10. So let me zoom in. So it starts off by kind of bouncing back and forth pretty far, but then as I can see, it doesn't take me too long before it starts getting much smaller in how it's hovering. And we can see it's just getting closer and closer. All of these numbers are getting closer and closer and closer to 0. They go a little bit above, or a little bit below, a little bit above, below, below. Okay, write that down. And so we can see why it makes sense then that the graph, or not that the graph, that the limit of this would just equal 0. Just spell it. Come on. This isn't an English class. I don't have time to tell you how to spell things. All right. Go to Miss Ward's office hours or whatever. Ask her. Okay. So this limit equals 0. It converges. All right, so whenever we have a converging sequence, if we graphed out those points, then it would look exactly like that graph had, where the points start off, either they're just nicely approaching, or maybe if there's the alternating positive negative deal, then it goes up, down, but then gets smaller, closer to whatever the actual number is, in this case 0. That's pretty close spelling, not quite, but whatever, it's good enough for now. Okay, so last couple things. These will go quick. A monotonic function. Right, sometimes we also call these a monotone function. But a monotonic function is either non-decreasing or non-increasing. So for a non-decreasing function, what that means is the derivative will always be greater than or equal to 0. Okay, so note that this is not saying, now you might think non-decreasing just means increasing, but that's not true. Because, so let's say I have something like this, okay, where this is not technically an increasing function everywhere, because at these points, my derivative is 0. Okay, but it doesn't change from decreasing. It's just that the derivative is 0. Negative, never negative. Well, man, I'm having a stroke out here. Okay. I can't even drink out of this. Right. So these points where the derivative is 0 exactly, but never negative. I still can't say it. Non-increasing f prime of x, that means the derivative is always going to be less than or equal to 0. So kind of a similar thing. So the function's going down, and then maybe it hits 0, but then continues going down, and maybe it hits 0, but then is going down. Oops, it doesn't turn up. Okay, so there are these points. If it would let me write in green. There are these points where the derivative is 0, but in this case, for non-increasing, the derivative is never positive. Okay, so monotonic functions. Can a function that's a straight line be doubly monotonic because f prime equals 0? That's a I think technically a horizontal line function is monotonic. We wouldn't say it's like doubly monotonic, because again, the definition of monotonic is it's one of these things. Only one of these things needs to be true in order to be monotonic. So it's not like we say specifically. I mean, we can talk about it, but we don't differentiate in how we say it when we say non-decreasing monotonic or non-increasing monotonic. Monotonic just means one of these is true. But I'm pretty sure that yes, that a monotonic function, the linear straight line, is a horizontal line. Yeah, I think that's what Reese was asking about, right? Yeah, that's what I was talking about, at least in terms of straight line, a horizontal line. I think it should be monotonic as well. I'll have to double check that, but my intuition would say yes. Bounded. So a sequence is bounded if the sequence is always between two numbers. Vertical. Did someone mean vertical? Someone talking about vertical lines? Okay. So bounded if it's always between two numbers, capital M and capital N. Okay, so every sequence of the term is between these two options, right? They'll never go outside of those bounds. And then a nice little theorem. So sometimes if we just want to determine, hey, does this sequence converge? Well, we can use this test. So if a sequence is monotonic and it's bounded, then we know for sure that it converges. So this is just a way that we can prove, yes, this sequence does converge. So we just have to figure out, is it bounded on either side, and is it monotonic? Okay, so I think our last thing, show theorem 8.5 applies to the given sequence, then find the limit to verify. Okay, so pretty straightforward example. So for example, if you need on these, just first think about what the sequence would actually look like. So A1, if I plug in 1, I get 1. I plug in 2, I get 1/2. 3, 1/3, 1/4, 1/5, etc. Okay. So I should be able to already see the maximum value that this sequence will ever be is 1. There's no number that I can plug in here because the only numbers we plug in are natural numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. So the maximum number this sequence will ever be is 1. Okay, so I know that 1 over n is always going to be less than or equal to 1. Now, on the other side, I should also be able to tell that this sequence will always be greater than 0. Because I'm still plugging in numbers here. You know, eventually I'll get to, like 1 over 13,421, and then 1 over 13,422, and etc. But the point is, there's always going to be some number in the denominator. So I'm always doing 1 divided by that number. Now, these will start to be really, 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 really small numbers, but they're still a number nonetheless. So I can state that 1 over n is bounded by 0 and 1. Right? And actually 1 over n will never hit 0. So it's bounded between 0 and 1. So in thinking about the theorem, is it bounded? Yes, it is. We know that part. Now, is it monotonic? Well, let's look at the derivative. Right, derivative of 1 over n. So remember, think about that as n to the negative first power. Does it count for bounded if it's just approaching? Yes. Because the point is, it'll still never be anything less than 0. Okay, so it is still bounded by 0. Yeah. It's a good question. So this would be negative 1 over n squared. So now let's think about negative 1 over n squared. Negative 1 over n squared, I'm plugging in natural numbers, 1, 2, 3, 4, 5. So those being squared, I mean, they're already positive, but then being squared, so they're definitely positive. But then there's this negative out in front. So that means every number that I plug in, right, the derivative will always be less than 0. Always. Right? Not 0, not positive, definitely not positive. Right? So the derivative of an will always be less than 0. Okay, which means that this is non-increasing, which then means it is monotonic. So the theorem applies. So we have now proved this sequence definitely does converge. Now we haven't proved exactly what it converges to, but we've proved that it does converge. And so it says to double check by actually finding the limit. So this is an easy limit to take, so let's just do that real quick. We didn't really need to use this theorem, but it's just good practice of seeing how it works. Okay. We should definitely be able to see that the limit of 1 over n, as n goes to infinity, is 0, which means that yes, it converges. So that's just a check to see that, okay, yeah, our theorem did work. So the theorem is good for just determining, does it converge at all? Right? The theorem will not tell us what it converges to specifically, but sometimes it'll be good for us to know just the fact that it does converge. We'll need just that information. We won't necessarily care specifically about what the actual number is it converges to, but it'll be useful for us to know that it converges in general. Ask your mom and dad. They should have the sign-out sheet. Or whoever's in the house. I don't know. You have a cat or something? Maybe them? Okay, so to use the theorem, figure out, gotta use some intuition on the bounded part, right? You can kind of test some numbers and see, okay, yeah, but just kind of have to think, right, yeah, it should definitely be between these two numbers because of whatever reasons. And then secondly, take the derivative, see if that derivative will be always non-increasing or non-decreasing, depending on if it's positive, negative, whatever. And so if both those are true, then we can say for sure that it does converge. Questions? Here's some practice if you want to do it. These are actually, I went and double checked these. So these are all good. Should be things that you can do. It's just practicing, taking limits, figuring out the rules, the explicit forms of the sequences, and then doing a little bit of using the theorem, determining if things are bounded or not, etc. Do you like streaming? Yeah, actually, so the kind of counterintuitive thing